Today, we're going to tackle a huge question in democracy. How do we build an election system that's not just secure, but that everyone can actually trust is secure? It's a wild journey, taking us from the humble paper ballot all the way to the cutting edge of cryptography. Let's dive in.
Okay, so at the heart of all this is one simple but, incredibly tough question. How can you be absolutely certain that your vote was recorded exactly as you intended and that it was included in that final correct tally? That is the core challenge we're unpacking today. For years, we've basically been stuck in this classic trade-off. On one hand, you've got traditional paper ballots. The problem? They can be physically lost, they can be destroyed, or they can just be miscounted by human error. But on the other hand, you have those direct recording electronic machines, which, like any computer, are vulnerable to software bugs and, of course, the threat of hacking. So yeah, neither one is perfect.
So, where do we even start? Well, the first and honestly the most intuitive solution is to ground the whole process in something you can actually touch. A tangible, auditable paper trail that you can hold right in your hand.
This quote right here, it gets to the very core of the psychology behind election trust. I mean, think about it. Digital data is abstract. It's just code. But a physical piece of paper? That's tangible evidence. It's something real you can hold, point to, and most importantly, verify.
And that's exactly why paper ballots are so fundamental. They give us a permanent record that can't just be erased by a power outage or some software bug. It's why experts call them the bedrock of secure elections. States like Florida and Ohio, they rely on them for this very reason, creating a verifiable system that is absolutely essential for any valid recount or audit.
But of course, there's a catch, right? Manually counting millions and millions of paper ballots is incredibly slow and, let's be honest, full of opportunities for human error. In a modern, high-volume election, waiting for days or even weeks for the results, well, that's just not practical. And it can create its own kind of distrust.
So that brings us right to our second solution, using technology not to replace paper, but to supercharge it. The goal here is to get the best of both worlds, all the security of a paper trail, but with the speed of a digital process. For a great example, just take a look at King County, Washington. Their old tabulation system was a serious bottleneck. It can only process about 1,500 votes per hour. When you've got hundreds of thousands of mail-in ballots piling up, that speed is a major problem. But now, get this. By bringing in modern, high-speed scanners, they boosted that rate all the way up to 18,000 votes per hour. And that's per scanner. We're talking more than a tenfold increase in efficiency. It turns what could have been a week-long count into a process that's done overnight. And these aren't just faster machines. These intelligent scanners use advanced imaging to accurately read ballots even if they're folded or smudged. What's really cool is they also automatically flag and sort any invalid ballots for a human to review, which means they're catching errors before they can ever compromise the count.
Okay, so we've got a secure paper record and a fast, accurate way to count it. That's pretty good. But what's next? What if we could take verification a giant leap further into the realm of pure mathematics, where literally anyone could check the final tally for themselves?
This is where we get into the really fascinating, cutting-edge stuff, end-to-end verifiable voting systems. The whole idea here is to build trust not just on what we can see, but on mathematical proof.
So, an E2EV system uses some pretty advanced cryptography to give each voter two incredible powers. First, the power to verify their own vote was recorded correctly. And second, the power to prove it was included in the final tally. And the amazing part is, it does all of this without ever revealing how you voted, so your privacy is totally protected. So how on earth does that work? Well, one of the key technologies is something called homomorphic encryption. The easiest way to think about it is like this. Imagine everyone puts their vote into a locked box. Homomorphic encryption lets you add up all the votes inside those boxes to get a final tally without ever unlocking a single one. You're literally counting the encrypted votes directly. All right, the next piece of the puzzle is something called a zero-knowledge proof. It's a way for the system to prove a statement is true, like, hey, the final vote tally is correct, without revealing any of the secret information behind it. In other words, the count gets verified for everyone to see, but individual votes stay completely anonymous. And this is the part that brings it all back to you, the voter. When you vote in a system like this, you get a unique cryptographic receipt. You can then go to a public but totally anonymous online bulletin board and use that receipt to see for yourself that your encrypted vote is part of the final count. It's personal, mathematical verification.
Pretty cool, right?
But, the race for security never, ever ends. Even this incredibly advanced cryptographic system faces a future threat, one that exists way out on the horizon of computing itself.
Okay, here's the challenge. The very same encryption that protects everything from our bank accounts to our elections is, at least in theory, vulnerable. A powerful enough quantum computer could, one day, break it. Now, these machines don't really exist yet in that powerful form, but we have to prepare for the day they might.
To really get the scale of this challenge, think about this. A problem that would take one of our current, classical computers billions of years to solve could potentially be cracked by a quantum computer in just a few hours. I mean, that completely changes the entire security landscape.
The good news is, cryptographers are already way ahead of the game, building the next generation of defense. The U.S. National Institute of Standards and Technology, or NIST, has been developing brand new cryptographic standards that are specifically designed to be quantum resistant. These new methods are based on totally different mathematical principles, and they really do represent the future of digital security.
What this all shows is that there's no single final solution to election security. It's not a one-and-done thing. Our systems have to be what's called crypto-agile, built from the ground up to adapt, evolve, and upgrade as new technologies and new threats emerge. You have to remember, security is always a moving target.
So, from the simple, humble paper ballot to the far-out frontiers of quantum computing, the goal has always been the same. The election of the future isn't just about who wins. It's about building a system so transparent and so verifiable that we can all trust the result. Because in a democracy, proving the outcome is every bit as important as the outcome itself.